Hello, and welcome to our NACL 2022 tutorial on self-supervised representation learning for speech processing. This tutorial will be given by Abdel Rahman, Hungi Lee, Shinji Watanabe, myself, Tara Sinop, Karen Leviscu, Shangwen Li, Xuan Yang, and Katrine Kirkov. A brief outline of the tutorial. First, we'll give a historical context of representation learning, followed by looking at speech representation learning paradigms. Next, we'll discuss benchmarks for self-supervised learning approaches, and then an analysis of self-supervised representations. We'll then talk about from learning representation learning to zero resources, and then topics beyond accuracy, and finally, toolkits for self-supervised speech representation learning. So first, let me begin by discussing what is SSL. So learning methods can be broken into two main categories. Supervised learning methods look to train models with labeled data. So over the past decade, deep learning has revolutionized the field of speech recognition, and supervised learning has played a very important part in this transformation. However, what this has meant is that for domains and languages that have little labeled data, they have not enjoyed the same successes with deep learning. So researchers have explored a variety of techniques to overcome the need for labeled data by exploring approaches that use unpaired audio-only data. So these sorts of methods are known as representation learning. And representation learning methods seek to develop algorithms which can extract latent features that capture underlying explanatory factors from an observed input. Representation learning can be broken into three main categories. In unsupervised learning, we discover patterns in data without pre-assigning labels. Examples of this include k-means clustering, mixture models, autoencoders, and non-negative matrix factorization. In semi-supervised learning, we use a small number of labeled samples to guide learning with a larger amount of unlabeled data. And finally, in self-supervised learning, this is a subcategory of unsupervised learning that refers to techniques that utilize information extracted from the input data as the label to learn representations useful for downstream tasks. So self-supervised learning will be the focus of this tutorial. This SSL framework can be broken down into two stages. In the first stage, as shown in the figure to the right, we use SSL to pre-train an upstream model. In the second stage, a downstream task uses the learned representation from a pre-trained model, frozen, or fine-tune the pre-trained model using unsupervised data. Examples of this include speech recognition and speaker ID. So what type of representation do we want? We want the representation that is learned to be one, disentangled. This means the spoken utterance have rich information, including speaker identity, style, emotion, and noise. So we want to make sure that these factors are disentangled. Number two, we want the representation to be invariant. So we want a representation that is robust to differences in background noise and communication channels. Number three, we want the representation to be hierarchical. That means learning a representation at the acoustic, lexical, and semantic level, which will allow us to use such a model for many different downstream tasks. Let's go on to the historical development of SSL. So first, we'll dive into the historical background in the context of three previous waves of research, namely in the 1900s, the first wave, the 2000s, the second wave, and more recently today, which we'll call the third wave. In the first wave, early work used simple clustering methods. So this included work where patterns were clustered semi-automatically using techniques such as k-means, and after which isolated words are recognized by finding the training cluster closest to the test data. Modeling text improved such that subword units were represented by Gaussian mixture models. While GMMs were first built for context-independent phonemes, state clustering algorithms then resulted in GMMs for context-dependent phonemes. Dynamic models like hidden markup models allowed for the processing of a continuous speech rather than isolated words. So these generative GMM and HMM models were trained by maximizing the likelihood of the data given the model. And they can be trained in both supervised and unsupervised way. Finally, extracting speech features from generative models, where the main goal was to use the knowledge learned by the generative model in some downstream task. This can include feature vectors derived from parameters of the trained GMM, and these downstream tasks for these features include speech recognition, speaker recognition, and language verification. The second wave includes stacked neural networks. So neural models allow for a much more diverse modeling of the input compared to GMMs. The techniques which became popular in the second wave were mainly applied to vision and NLP and inspired speech tasks. These include techniques such as the restricted Boltzmann machine, denoising autoencoder, noise contrastive estimation, and sparse coding. So higher capacity networks were achieved by building deep networks with multiple layers, which could capture more high-level representations. Finally, the third wave, a more recent trend, is to learn networks that map the input to the desired representation by solving what we call a pretext task. And this has the following characteristics. Number one, all layers are trained end-to-end to optimize a single pretext task instead of relying on layer-wise pre-training. Number two, stacked networks typically only had a few layers, but deep networks are much, much more common now. And number three, the representation should be evaluated on many tasks. So for NLP, the eval set could be GLUE, which compromises 9 tasks, or for speech, it could be SUPERB, which is 10 tasks. A very important part of the third wave is the design of a pre-task, and this allows the model to efficiently use knowledge from unlabeled data. So for example, this could include generating an object from partial information for vision tasks. Using previous tokens in the sentence predicts the next token. Examples include Elmo, GPT, Megatron, or also contrastive learning.